So as I summarize the separation of variables using spherical coordinates, remember I wrote u of r, theta and phi to be r of r, s of theta, q of phi. Then q would satisfy a standard problem, but r would satisfy the spherical Bessel equation. And q would satisfy a standard problem, and s would satisfy the Legendre equation if you do the transformation x is cosine of theta. Okay, so we have everything in a nutshell right here. Now here is given the spherical Bessel equation, equation 7.31, where the separation constant lambda had been written to be n times n plus 1. And it's called spherical Bessel equation because it can be solved using Bessel functions. And I'll just show you the solution here on the next slide. So here's the spherical Bessel functions of order n of the first kind, which is a little j n. And this is root of pi divided by 2x. And then the standard Bessel function j n plus 1/2 of x. So from the Bessel functions capital J, which we learned about already, we can then make these spherical Bessel functions multiplying with this factor root of pi divided by 2x. For the Bessel functions, we have the big J and the big Y. So for the spherical, we have the little j and the little y. Where's the little y then? So then here, the second kind spherical Bessel functions are given by the second kind Bessel functions. All right, so that's that. And then down here, I give you some explicit examples for these functions. So on the left, the first kind spherical Bessel functions. On the right, the second kind spherical Bessel functions. Okay, let's keep this at that. Let's come back here. So now let's look at the Legendre equation and the Legendre solutions for the S problem. The Legendre differential equation is given here in theorem 7.2. It's 1 minus x squared second derivative minus 2x first derivative plus lambda v is equal to 0. And then the solutions are called Legendre functions or Legendre polynomials, Pn. Again, we have first kind and second kind, so here are the formulas for the first kind, and these are all polynomials. So these are called the Legendre polynomials. Okay, P0 is super simple. It's just the function 1, so the constant 1. P1 is the linear function x. So okay, it starts rather easy. And then the higher you go, the higher order polynomial you get. So P2 is a parabola, P3 is a cubic, P4 is a quartic, P5 is quintic, and so on. And here I plot them out. P0 would be the constant function here, P1 would be the linear function there, where's the parabola there, so this would be P2, and then which is a third order, this is a third order one, P3, and I think the fourth order would then be this one, P4, because it has exactly 4 zeros. So this is how they look like. Again, there's a little bit of a similarity with sine and cosine because they oscillate a lot. But these are polynomials. They only have a finite number of zeros, unless sine and cosine. Here is a wonderful general formula, 7.11, where you can compute all of the Legendre polynomials if you wish to do so. Now, further, we can show that these Legendre polynomials are orthogonal. So then we can do the same thing with the generalized Fourier series expansion. So then we call it a Legendre polynomial expansion. And we can use superposition and proceed in our solution of the PDE. Notice here, maybe I go back here. Notice here these polynomials, if we use them, we always have in the back of our mind the transformation that x is cosine of theta, all right? So in these polynomials, wherever is x, you would actually sub in cosine of theta. Remember that I had this wonderful generator of Bessel functions, and you might wonder if I have a similar thing for Legendre polynomials. And I do have a Legendre polynomial generator, which is this one here. So it's spherically symmetric, and I can hit it and make all kind of noises. I can bounce it. And so what you then hear, these are indeed spherical Bessel functions and Legendre polynomials. If you ever have been to a basketball game, for example, where then at the beginning of the game you hear like 30 balls being bounced in the gymnasium. It makes a racket, it makes so much noise. And this is an assault of Legendre polynomials. All right, so if you're really motivated, then I leave it up to you to find the corresponding eigenfunctions for this object here.